Hello, science fans! Today, we're diving into a really important topic in the world of medicine. It's called filter integrity testing. Now, that might sound like a mouthful, but the idea is actually pretty simple and super cool. Imagine you're making a special drink, like a medicine that needs to be perfectly clean. You wouldn't want any tiny, unwanted things like germs or dust getting into it, right? To stop those things, scientists and engineers use special filters. These filters are like superfine kitchen strainers, but on a microscopic level. They are designed to catch incredibly small particles, especially bacteria, to make sure the medicine is safe to use. Filter integrity testing is our way of checking to make sure these filters are working perfectly. So, what does integrity mean here? It means the filter is whole, strong, and doesn't have any hidden damage. Think of it like checking a window screen for holes before summer. If there's a tiny rip, a mosquito can get in. In medicine, if a filter has a tiny tear or a pore that's too big, a dangerous bacterium could get through. That would be very, very bad for the person taking the medicine. So before and sometimes after we use a filter to make a batch of medicine, we run a special test on it. This test doesn't check if the medicine is good. It checks if the filter is good. It's a critical safety check, a scientific double check to protect people's health. The importance of this process cannot be overstated. Consider this. Many modern medicines, especially those given through an IV drip directly into someone's bloodstream, must be completely sterile. Sterile means they are 100% free of living germs like bacteria or fungi. If even a few of these tiny invaders get into the medicine, they could cause a serious infection in a patient who is already sick. This could make them much sicker or even be life-threatening. Filter integrity testing is the last line of defense. It's the final confirmation that our filtration process worked exactly as planned and that the medicine we are about to give someone is as clean and safe as science can possibly make it. This guide is all about exploring these amazing tests. We're going to break down how they work in a way that's easy to understand. We'll look at the different types of tests, what they measure, and what the results tell us. You'll see that it's all based on some really neat principles of physics and chemistry. By the end, you'll understand why this careful, precise testing is a cornerstone of modern pharmaceutical manufacturing. It's a fantastic example of how science is used every single day to keep us all safe and healthy. So, let's get started on our journey into the world of filter integrity testing. Let's talk about how these amazing filters actually work. It's not just like a pasta strainer. Pharmaceutical filters are made of special materials, like polymers, and are designed with a very specific, tangled structure. Imagine a super dense forest of tiny fibers. When a liquid medicine is pushed through this material, the liquid molecules are small enough to wiggle their way through the gaps in the forest. But bacteria are much bigger. They are like big, clumsy bears trying to get through that same dense forest. They get stuck. This process is called size exclusion. The filter's pores, or the tiny openings between the fibers, are manufactured to be smaller than the smallest known bacteria, which is typically around 0.22 micrometers. But that's not the only way they work. There's another cool science principle at play called adsorption. Think of it like static cling. The surfaces of the filter fibers can have a slight electrical charge. As the liquid flows by, bacteria and other particles can get stuck to the filter material, almost like a sock sticks to your shirt when it comes out of the dryer. This adds an extra layer of protection, grabbing onto germs that might otherwise be small enough to squeeze through. So it's a combination of physically blocking them and electrically grabbing them. This dual action makes these filters incredibly effective at making liquids sterile. Now, why do we need to test them? Because these filters are delicate structures. They can be damaged in many ways. Maybe the filter was dropped during shipping, or maybe it was installed incorrectly into the filtration system. Sometimes, a very high pressure or a very hot cleaning process can create a tiny weakness or a tear in the filter material. Even a flaw that is too small for the human eye to see can be a huge problem. A microscopic tear could create a pathway that is bigger than 0.22 micrometers, allowing bacteria to sneak through into the final product. Testing is our way of finding these invisible flaws. This is where the idea of integrity comes back into play. An integral filter is one that is structurally sound and meets its design specifications perfectly. It has no defects, no oversized pores, and no damage. The tests we're going to talk about are designed to challenge the filter in a non-destructive way. They use air or water pressure to probe the filter's structure and confirm that its largest pores are still smaller than the minimum size required to stop bacteria. It's a clever way to ask the filter, "Are you okay? Are you ready to do your important job of protecting patients?" Without this confirmation, we would just be guessing. And in medicine, guessing is never an option. One of the oldest and most common tests is called the bubble point test. The name gives you a great clue about how it works. It's all about finding the weakest link in the filter, which is its largest pore. To do this test, we first need to get the filter completely wet with a liquid, usually water or alcohol. Every single tiny pore in that filter membrane needs to be filled with the liquid. The liquid is held in these pores by a force called surface tension. It's the same force that lets you slightly overfill a glass of water, creating a little dome on top without spilling. The liquid molecules are holding onto each other and the sides of the pore. Once the filter is thoroughly wetted, we connect it to a source of pressurized gas, like clean air or nitrogen. Then, we slowly, very slowly, start to increase the gas pressure on one side of the filter. At first, nothing happens. The surface tension of the liquid in the pores is strong enough to resist the gentle push of the gas. But as we keep increasing the pressure, we're putting more and more force on that liquid. Eventually, the pressure will become strong enough to overcome the surface tension in the largest pore. Why the largest one? Because it has the weakest grip on the liquid. Think of it like blowing a bubble with a wand. It's easier to make a bubble with a big loop than a tiny one. The exact moment that the gas pressure pushes the liquid out of that largest pore, and a steady stream of bubbles appears on the other side, is called the bubble point. We measure the pressure at that exact moment. Every filter model has a specific minimum bubble point value that it must meet, which is determined by the manufacturer. For example, the manufacturer might say that for this filter to be good, its bubble point must be at least 50 psi or pounds per square inch. If our test shows a bubble point of 52 psi, that's great. It means the largest pore is even smaller than the maximum allowed size, and the filter passes the test. But what if we see a steady stream of bubbles at a much lower pressure, say 30 psi? That's a bad sign. A low bubble point tells us that there is at least one pore in the filter that is too big. It could be a small tear, a manufacturing defect, or some other kind of damage. That oversized pore is a potential pathway for bacteria to get through. So, a filter that fails the bubble point test must be discarded. The entire batch of medicine that was filtered with it might have to be thrown out as well, because we can no longer guarantee it is sterile. This simple test, based on the physics of bubbles, is a powerful tool for ensuring medicine safety. The forward flow test is another very popular and reliable method for checking filter integrity. It's a bit different from the bubble point test. Instead of looking for the exact pressure that makes bubbles appear, this test measures how much gas moves through the filter at a constant pressure. Just like the bubble point test, we start by completely wetting the filter membrane with a suitable liquid, like purified water. This fills up all the pores and sets the stage for our scientific measurement. The principle we are using here is based on a law of physics called Fick's law of diffusion, which describes how particles move from an area of high concentration to low concentration. After wetting the filter, we apply a constant gas pressure to one side. This pressure is set to be high, but still below the filter's known bubble point. At this pressure, the gas isn't strong enough to push the liquid out of the pores and create a stream of bubbles. However, some of the gas molecules will actually dissolve into the liquid on the high-pressure side, travel through the liquid held in the pores, and then come out of the solution on the low-pressure side. This very slow, steady movement of gas through the wet filter is called diffusion. We use a very sensitive machine to measure the rate of this gas flow. The amount of gas that diffuses through the filter is directly related to the surface area of the filter membrane. A larger filter will naturally have a higher diffusion flow than a smaller one, even if they are both perfectly intact. The filter manufacturer does extensive testing and tells us the maximum acceptable flow rate for a specific filter size and type. For example, they might say that for a 10-inch filter cartridge at a test pressure of 40 psi, the forward flow rate should not be more than 20 milliliters per minute. Our testing machine measures this flow, and if the result is 15 milliliters per minute, the filter passes. It's integral and ready for use. If the measured flow rate is higher than the manufacturer's limit, let's say 40 milliliters per minute, it indicates a problem. This high flow rate means that gas is moving through the filter much faster than it should by diffusion alone. This is a strong sign that there is a flaw, like a tear or an oversized pore. The gas is no longer just diffusing, it's actually flowing in bulk through a defect. This is called bulk flow, and it's exactly what we don't want to see. A failed forward flow test means the filter's integrity is compromised, and it cannot be trusted to produce a sterile product. This test is highly automated and gives a precise numerical result, making it a favorite in the pharmaceutical industry. You might hear people talk about the diffusion flow test and the forward flow test, and it can get a little confusing. The truth is, they are very closely related. You can think of them as scientific cousins. In fact, many people use the terms interchangeably. Both tests operate on the exact same principle. They measure the slow movement of gas molecules through a liquid-wetted filter membrane at a pressure below the bubble point. This movement, as we discussed, is called diffusion. The goal for both tests is to confirm that the filter is structurally sound and doesn't have any holes or defects that would allow for bulk flow of gas. So, what's the difference? The main distinction often comes down to the size of the filter system being tested. The term diffusion test is sometimes used specifically when testing smaller filter systems, like those used in a laboratory or for small-scale production. In these smaller systems, the total amount of gas that moves through the filter by diffusion is very, very small. The flow rates are tiny, because the flow is almost purely diffusive, and the contribution from any potential bulk flow through the pores is negligible for an intact filter. The name diffusion test is a very accurate description of what is being measured. On the other hand, the term forward flow test is often applied to larger filtration systems, like those used in full-scale manufacturing that might involve multiple large filter cartridges. In these big systems, the total surface area of the filter membrane is huge. Even with a perfectly integral filter, the total amount of gas diffusing through is significant. The name forward flow is a more general term that encompasses this total flow of gas moving forward through the system. It's still measuring diffusion, but it acknowledges that on a large scale, we are measuring the total forward movement of gas, which is primarily diffusive. Regardless of the name used, the procedure and the pass or fail criteria are the same. You wet the filter, apply a constant pressure below the bubble point, and measure the resulting gas flow rate. You then compare this measured rate to the maximum allowable limit specified by the filter's manufacturer. If the measured flow is below the limit, the filter passes. If it's above the limit, it fails. So whether you call it a diffusion test or a forward flow test, you are performing a highly sensitive and quantitative check on the filter's integrity, ensuring it is fit to produce safe and sterile medicines. Now let's talk about a special kind of filter and a special kind of test. Some filters are hydrophobic, which basically means they are water-fearing. If you try to push water through a dry hydrophobic filter, the water is just repelled by the filter material. It won't wet the membrane easily. These filters are super useful for applications like sterile venting, where you want air to pass through freely, but need to block any water droplets or airborne bacteria. Since we can't easily wet these filters with water to perform a bubble point or forward flow test, we need a different strategy. That's where the water intrusion test, or WIT, comes in. The water intrusion test cleverly flips the script. Instead of wetting the filter with a liquid and pushing gas through it, we keep the filter dry and push water against it. We apply water pressure to one side of the dry, hydrophobic filter membrane. Because the filter repels water, the water can't easily pass through the pores. However, under enough pressure, a very tiny amount of water can be forced into the pores of the filter membrane without actually passing through to the other side. This isn't a bulk flow of water, it's more like water vapor penetrating the pore structure. This tiny loss of water from the pressurized side can be measured. The test procedure involves putting water on one side of the filter and air on the other. Then, we increase the pressure of the water to a specific test pressure. The testing machine measures the rate at which the water volume on the pressurized side decreases. This decrease is due to the water being forced into the filter's pore structure. For a good integral hydrophobic filter, this rate of water intrusion will be very low and stable. The manufacturer provides a specification for the maximum amount of water intrusion allowed for a given filter type and size at a specific test pressure. If the filter has a defect, like a tear or a pore that's too large, the water will not just intrude into the pores. It will actually flow through the defect to the other side. This would result in a much faster and larger loss of water volume on the pressurized side. If the measured water intrusion rate is higher than the manufacturer's limit, the test fails. This tells us that the filter's hydrophobic character has been compromised or that it has a physical flaw. The water intrusion test is a brilliant, non-destructive way to confirm the integrity of these special water-fearing filters, making sure they can do their job of letting air in while keeping contaminants out. The pressure hold test, also known as the pressure decay test, is another common and straightforward method for assessing filter integrity. It's kind of like checking a bicycle tire for a slow leak. The basic idea is to pressurize the system and see if it can hold that pressure over time. This test is often considered a simpler alternative to the forward flow test because it doesn't require a sensitive flow meter. Instead, it relies on a highly accurate pressure gauge. It works on the same underlying principle as the forward flow test. Gas will diffuse through a wetted filter membrane. The test begins, just like many others, by thoroughly wetting the filter with a liquid. Then, we pressurize the upstream side of the filter housing with a gas, like air or nitrogen, to a predetermined test pressure. This pressure is typically the same one used for a forward flow test, which is around 80% of the filter's expected bubble point. Once the target pressure is reached, the gas supply is shut off, isolating the system. We then start a timer and carefully monitor the pressure in the system. Because gas is slowly diffusing through the wetted membrane, we expect to see a small gradual drop in pressure over the test period. The key measurement here is the amount of pressure that's lost over a specific amount of time, for instance, over a 15-minute period. A sound integral filter will only allow a very small and predictable amount of pressure decay due to gas diffusion. The filter manufacturer provides a specification for the maximum allowable pressure drop for a given filter, test pressure, and upstream volume. The upstream volume, the space on the pressurized side of the filter, is really important here, since a larger volume will show a smaller pressure drop for the same amount of gas loss. If the measured pressure drop is greater than the manufacturer's specified limit, the test fails. A rapid or excessive pressure drop indicates that gas is escaping the system faster than it should by diffusion alone. This points to a leak in the system. The leak could be from a non-integral filter, a tear or an oversized pore, or it could be from a bad seal or a loose connection elsewhere in the test setup. This is an important point. A failed pressure hold test requires investigation to pinpoint the source of the leak. But as a screening tool, it's a very effective way to confirm that the entire filtration system, including the filter itself, is properly sealed and integral. So, what happens when a filter integrity test fails? The first and most important rule is to stop and investigate. A failed test is a red flag that just can't be ignored. The immediate consequence is that the filter in question cannot be used, or if it was a post-use test, the batch of medicine that was just filtered is now considered suspect. It cannot be released for patient use until a thorough investigation proves that it is safe. This is a critical control point in pharmaceutical manufacturing, and honestly, patient safety is always the #1 priority. The batch is quarantined, and the science detectives get to work. The investigation process is a systematic search for the cause of the failure. The first step is often to check the test setup itself. Was the test performed correctly? Was the filter wetted properly? Sometimes incomplete wetting can lead to a false failure because air pockets can allow gas to flow through easily. We also check the equipment. Is the pressure gauge calibrated? Are all the hoses and connections tight? A leak in the testing apparatus can mimic a failed filter. It's essential to rule out these external factors before concluding that the filter itself is the problem. If the test setup and procedure are confirmed to be correct, the focus shifts to the filter itself. The filter might be retested to confirm the failure. If it fails again, it is definitively non-integral. The cause could be a manufacturing defect that slipped through quality control, or it could be damage that occurred during shipping, handling, or installation. Sometimes the filtration process itself, with high pressures or aggressive chemicals, can damage the filter. Finding the root cause is crucial, not just for deciding the fate of the current batch, but for preventing the same problem from happening again in the future. Common problems that lead to test failures include using the wrong test parameters, like an incorrect test pressure or time. Incomplete wetting is a frequent culprit, especially with large or tightly packed filters. Another issue can be temperature fluctuations during the test, which can affect gas pressure and volume, leading to inaccurate results. By understanding these potential pitfalls, operators can take care to perform the tests correctly every time. Troubleshooting a failed test is a critical skill that ensures the integrity testing process is itself reliable, providing a true and accurate assessment of the filter's ability to protect patients. As we've seen, filter integrity testing is much more than just a routine check. It's a fundamental pillar of modern medicine safety. It's a practical application of physics and chemistry that stands as a guardian between the manufacturing process and the patient. Every time one of these tests is performed, it's a deliberate act of ensuring quality and protecting health. From the simple elegance of the bubble point test to the precise measurement of the forward flow test, each method provides a unique window into the microscopic world of the filter, confirming that it is whole, sound, and ready to perform its critical duty of sterilization. The rules and regulations set forth by global health authorities like the US Food and Drug Administration, the European Medicines Agency, and the World Health Organization underscore the global consensus on this matter. These agencies mandate that sterile products produced by filtration must be checked with an integrity test. They require manufacturers to validate their testing methods and to document every test result. This regulatory framework ensures that every company, no matter where they are in the world, adheres to the same high standards of safety, creating a reliable global supply of safe medicines. The ultimate goal of all this science, technology, and regulation is you. It's about making sure that when you or a loved one needs a medicine, you can have complete confidence that it is pure and safe. It ensures that the medicine will help you heal, without introducing a new danger like a bacterial infection. The careful, methodical work of the scientists and technicians who perform these tests every day is a vital part of the healthcare system that often goes unseen. They are the quality guardians working behind the scenes to make modern medical treatments possible and safe. So the next time you think about modern medicine, remember the humble filter and the rigorous tests that prove its strength. It's a powerful story of how we use scientific principles to control the microscopic world for our benefit. Mastering filter integrity testing isn't just about following rules. It's about upholding a promise. It's a promise to every patient that their health and safety are our highest priority. By ensuring the integrity of our filters, we ensure the integrity of our medicine, and in doing so, we help build a healthier world for everyone. And that's a pretty amazing thing for science to do.